Hello again. Thank you for watching and studying math with me. This video is about formulas and literal equations. A literal equation has more than one variable in it. Let's begin with an example. This is the formula representing the relationship between Fahrenheit and Celsius temperature scales. Once I was doing a project where I flew every week to Montreal. Chicago uses Fahrenheit, Montreal Celsius. So let's do a couple of examples. So suppose I woke up in Montreal and they said it was going to be 30 degrees outside. They were talking Celsius, so what did that mean? So I am going to substitute in here 30 for C and see what the Fahrenheit reading would be, which is what I'm more used to. So the Fahrenheit reading would be equal to 9 over 5 times the Celsius reading, which they said was 30, plus 32. So what would happen then is 5 will go into 5 once, 5 will go into 36 times, so it's going to be 54 plus 32, and that means it was going to be 86. So if I were thinking about 30 degrees Fahrenheit, that would be a cold day, but 30 degrees Celsius, it is quite a warm day. Let's suppose that I woke up in Chicago and the temperature was 41 degrees. So I will substitute 41 for F, and I wondered if my friends in Montreal were having exactly the same weather, what would the temperature there be? So what I'm going to do is I'm going to solve for C. So I'm going to subtract 32, and I will get 9. When I subtract 32 from both sides, and then over here I'll have 9 over 5C. So what I'm going to do is multiply both sides by 5 over 9 to cancel that, and I will see that the Celsius reading is going to be 5 degrees. And so I would be putting 86 in such a table, and I would be putting 5 in such a table. Although I picked nice numbers, clearly there could be decimals involved. Okay, this is also a literal equation, even though I was using it as a formula in that one. Let's look at solving some other literal equations. In the first problem, I'm supposed to ask, I have theta is equal to k times a plus lambda. And this is an equation that comes up apparently in robotics, but I want to solve for lambda. So what I'm going to do is subtract Ka from both sides, and then I'm going to have equal to lambda, and that's the end of the story because I have lambda all by itself. The next example is a little bit more complicated. This comes up in economics, and we want to solve for lowercase p. Now notice we have a capital P that means something different. So the first thing I would do on the second example is distribute on the right-hand side. So capital P is equal to n times lowercase p minus nc. So I'm going to subtract the, add nc to both sides. Now capital P plus nc is equal to n times lowercase p. I want to solve for lowercase p, so lowercase p then is equal to capital P plus nc, all divided by n. These are examples of literal equations. Let's look at two more examples. Here, suppose I wanted a general purpose formula for centigrade in terms of Celsius. I would solve for the C. So first thing I would do is subtract the 32 from both sides, and that would be 9 over 5C. But like I did in the previous example, I will multiply both sides by 5 over 9 to get C on this side, and this will be 5 over 9. But it is 5 over 9 times the whole of F minus 32. So that would be solving for Celsius in terms of Fahrenheit. I often give this problem to students, and here both those p's are the same. And so when I'm solving for this, what I'm going to do is I'm going to use the distributive property in reverse and say, oh, this is really p times 1 plus rt. And so if I'm solving this one for p, I solve for c over here. Over here I say solve for capital P. Then I will get P is equal to A, and I divide both sides by the 1 plus RT. Now, in class, we'll work several problems, but serious students will want to carefully read the section and examples and do as many problems as possible. Until then, remember that time is precious. Each day must count. Doing the math will make you strong. Take care and see you in class.